Good to go?
Yep.
All right. So, as Dave said, I'm Trey German. I work down at Texas Instruments. So, you've probably heard of TI before, right? You've used our calculators, right? So, that's what a lot of people know us for, is our calculators. But we do so much more. In fact, that's one of our smallest business segments. What we really do the most of is make little chips. So, like all the chips you see on these boards here, well, not all of them, but a lot of them were made by Texas Instruments. So, a little background on myself. I'm 26, so I've been out of college now for, I guess, let's see, five or 6 years now. I went to college for computer engineering. I grew up really doing a lot of stuff like this. You know, I would buy kits and solder them together, and maybe I wouldn't understand everything, but I would pick up bits and pieces. And so then when I went to college, it was really great because I had all this pre-existing knowledge. I didn't necessarily understand how everything kind of fit together, but then college gave me that foundation, and I was able to integrate a lot of those things that I had learned as a kid that I didn't necessarily understand, but I was able to integrate them, and it really made me into the engineer that I am today. And so I like to kind of think of myself as a jack of all trades. I do a little bit of software work, I do a little bit of hardware work. You know, I've brought up processors when they first come back from the fab. So, you know, I've been one of the first people to actually touch a chip before. And that's a really cool feeling, to be able to be the first person to touch a chip and to bring it up and to make sure everything works. So that's a little background on kind of how I got my start. What I do kind of day to day is I'm actually on our software team. Even though you see all these circuit boards that I work on, I'm on our software team. So I work in a group called C2000, and C2000 is a digital real-time controls processor. So just like probably some of you guys are working with microcontrollers, maybe Arduinos or Launchpads or things like that, I work on little chips like that. So chips you can program that have inputs and outputs and A to D converters and PWMs and all that kind of stuff. So I write or work on the software that people like you or other professional engineers would use to actually program these guys. So driver libraries, header files that allow you to access registers, things of that nature. Beyond that, like I said, I also do a little bit of hardware, and that's kind of really what I want to talk about more than anything else, because I think it's more exciting. I like to kind of build something and then have something to show for it. Software can do a lot of cool things, but people, on the whole, they don't appreciate it as much as they should. Software definitely is important. It makes everything work. But if you go to someone and you're like, okay, I wrote this piece of software, that's cool. But if you go to someone and you're like, I built this quadcopter, they're like, whoa, right? Because they can actually, it's a tangible item. So that's kind of why I like doing hardware a little more than software. But don't get me wrong, software is very important, and you know, it's a skill you need to have if you're going to go into a career like this. So beyond that, I'm just going to kind of ramble here for a second. I didn't have a real plan. But so initially in school, I wanted to get into hardware, and you know, I came out of school in 2009, and in 2009 it was really hard to get a job. And so I actually started working for a small software company, and I did software for a communications peripheral called CAN. So have any of you guys ever heard of CAN before? It's a very ubiquitous serial kind of network protocol, if you will, or network interface. So CAN is actually what's used in your automobiles and your cars for all the different pieces to talk to each other. So, you know, you've got your engine, the engine computer, you've got, you know, body computers and sensors. They all communicate over a network called CAN. And so I did a lot of software in this company called Msp430 regarding CAN. And so I did bootloaders. Have you guys ever heard of a bootloader? Do you know what a bootloader is? No. So a bootloader is a piece of software that actually allows you to reprogram a chip in the field. So let's see, what's a good example of this? Let's say you bought a piece of consumer electronics hardware, like let's say like a wireless router, right? There's actually a bootloader in there, and it's one of the lowest level pieces of software on that device. And what it allows you to do, right, is you upload a new firmware file, and then it reprograms itself. So that's what a bootloader does. What I was doing in this company was actually writing software that would allow us to reprogram these chips over the CAN automotive kind of network interface. So that was cool. It was a great learning experience, and I kind of really learned a lot about software there. And so then I actually got hired into TI, and I moved back down here. So I actually grew up in Houston, so I'm a local Houston kind of guy. You know, I got hired into the software team and started writing software at TI. But once again, coming back, I really like to do hardware, and I was on this software team, and I wasn't getting to do hardware. So I made that known. I told my boss, I was like, doing software is good, but I really want to kind of get my hands dirty with some hardware too. And they were very nice, and oftentimes your boss won't be this nice, or your employer won't be this nice, but they actually, they allowed me to kind of do a little bit of hardware too. And so that's definitely something you want to look for in an employer. You want someone that's going to kind of work with you to kind of further your career goals. That's very important. And I've been very blessed in the fact that TI has done that for me. So that's a very good thing. So with that, let's I guess kind of dive into some of the stuff I've done, and we'll talk about the mistakes I've made, the things I've learned from it, and just kind of how everything happened. So the Launchpad. So have you guys ever heard of the Launchpad before? No? Okay. You've heard of Arduino before, yeah? Okay, there we go. So the Launchpad is very similar to the Arduino, right? It's a low-cost microcontroller development board. So you've got inputs, outputs, A to D converters, all that kind of good stuff. And all these boards are, like I said, super cheap, low cost. So they range anywhere from like $10 to I think $17 on the high end. And so how this all came about was I had actually designed a little circuit board that I wanted to get manufactured. So I saw one of the chips that I was working on. I was like, okay, this would make a great development platform. I want to make something that other people can use to make projects with. And so I designed this little circuit board. So it was like a little USB stick, just like a thumb drive, but it had one of our processors on it and a programmer. It had USB connectivity. It had an SD card reader on it, a whole bunch of other cool stuff. And I showed it to my management. They're like, "Whoa, this is cool, but it's not exactly what we're looking for." But that's kind of how I was able to show them that A, I wanted to do hardware, and B, I knew what I was doing when I was doing hardware, because I actually had a design, albeit it was on the computer, but I was able to show them that I had this capability, and that was an important first step to kind of changing my job description from purely software to being software and a little bit of hardware as well. So from that, the marketing people, and marketing people you'll find they're important people to know and to work with, but they'll throw wrenches into your plans all the time. So, but they were helpful in this instance, right? So they saw this design and they saw, okay, this is good. How can we leverage Trey's skills to further our business purposes? And one of the things you'll realize once you get into industry is it's all about business. Engineers, we tend to be kind of idealistic and do it for the fun of the technology, and we want to make the best technology out there. But in the end, you got to get paid, and to get paid, your company has to make money, right? So what we did is we kind of transformed that idea into something more along the lines of an Arduino. So the idea was to do kind of an Arduino Launchpad spin of my board that I had originally designed using a slightly different processor, a lower end processor. And so with that, the Launchpad RT was born. So one of the first prototypes of this board is this PCB right here. And so the Launchpad RT stands for Launchpad Real Time. And the C2000 processors that I work on are really good at digital real-time control applications. So that probably means nothing to you right now, but let me explain it real quick. So digital real-time controls, what that is basically interacting with the physical world, the analog world, very quickly in real time. So basically, if something happens, you're able to respond to that stimulus very, very quickly. And so the type of applications that these chips are used in are typically things like power supplies. So there's kind of two different types of power supplies, typically linear power supplies and switching power supplies. Switching power supplies are very efficient, and that's what most of the power supplies that you see and that you interact with, that's the technology they use. So the way those work is there's, let's draw a picture. So typically there's, you've got some voltage source. And then I'm probably going to screw up the topology, but you'll get the idea. So there's typically like an inductor, some type of switch. And so this might be connected up to your microcontroller, right? This is like the gate, or the gate of the MOSFET. And then you might have a diode and a capacitor. So what this allows you to do, I think this is a boost. Yeah, this is a boost. So this is what's called a boost converter. And you've got some nominal voltage here, let's say maybe 3.3 volts. And by switching this transistor on and off, you basically charge and discharge this inductor through this diode. So current only flows this way. And you charge up this capacitor to a higher voltage. So you might want, say, 12 volts out here. So the way that our chips would interface with this, right, you would have some voltage sense here. So this would go to your like A to D converter. And then this would be one of your PWM outputs. So you would have like a PWM. You guys know what PWM is? No. Pulse width modulation. So you have a square wave like this, right? Just a standard square wave. You know what a square wave is, yeah. So this square wave here has a 50% duty cycle, right? Duty cycle? Yes? No? Yeah? Okay. Good, good, good. I'm seeing some yeses there. So for instance, a square wave like this, still a square wave, not very square looking, but it's a square wave. This might have like a 10% duty cycle. And so by changing the duty cycle, this is effectively what a PWM does. It allows you to change the duty cycle of a square wave. By changing that duty cycle, you can effectively adjust the voltage you get out here. So if you put a control loop between these two things and you say, okay, I want my output to be 12 volts, and you compare your output that you actually have to like a set point, and then you run a control loop, you can actually change the duty cycle and actually statically get out the 12 volts you want. So long story short, that's a basic application that C2000 is used for, and that's why I called it the Launchpad real time. So this was actually one of the first prototypes. You guys can pass these around. So I've got a couple here you can pass around and kind of take a look at there. So I worked on that, and actually, people liked it. People in the group saw value in it. And so what we did is we started talking to a contract manufacturer in China. And this was a completely new experience for me, right? I had up to this point, I had built lots of circuit boards, but I had never actually taken anything all the way to production. And so this was a great experience for me, and I learned a lot from it. There was a lot of pain involved working with the Chinese contract manufacturer, simply because there's a lot of cultural differences, first of all. There's time differences, right? They're awake when you're asleep, and you're asleep when they're awake. So you have to have conference calls and stuff like that early in the morning or late at night. And then there's also regulations you have to deal with, trade laws, customs, things like that. And so that was another big headache in this project. So we worked with that contract manufacturer, and we got to the point of this board here. So this was actually a pre-production prototype. And so at this point, we had decided to call the board Control Pad. And so I'll go ahead and pass this one around. So this was actually fabricated and assembled in China. And this is actually one of the last ones I have left, because we sent some out to other people, but you can pass that around. And take a look at it. Let's see. So we got to this point, we were actually ready to go to production, and we had actually gone to production. So we had said, okay, let's make these boards. We're gonna order a bunch of them. Well, at that point, marketing came, and they're like, okay, we need to change this a little bit. You know, we want to fit it more in line with our business strategy. And so what happened is, at this point, the Msp430 Launch Pad, which is the original Launch Pad, which looks very similar to that, and actually I should have brought one, but I didn't. It had been out for a couple of years, and marketing came and they said, okay, we actually want to make your board into a launch pad. And so you'll notice that on those boards there, they've kind of got a single row of header pins on the side. And I'm going to go ahead and show you guys the actual final C2000 launch pad here. Oh, yeah. So this is a 430 launch pad. You guys can pass this around and kind of look at the similarities between the two boards. They said, you know, we want to change it into the C2000 launch pad. And so with that, we kind of had to redesign kind of where all the pins were, the branding on the board, the silk screening, all that. And so that took some time. But this is what ultimately came out of it. Excuse me. And so after some time kind of massaging the design a little bit, we came out with that board, and we went to production with it, and actually in August of last year, that board was released. So that was a big milestone in my career. I had an actual board that had gone to production, and I had actually taken it all the way from basically concept through schematic and layout, you know, doing all the silk screen, all the kind of marketing work at the board level, and then taking it to production with a Chinese contract manufacturer. And that was a big project. It took a lot of work, a lot of hard work. But in the end, right, you see it out there and you see it on the internet, and really I think the most satisfying part is when you see other people doing projects with your board. And that's really a great feeling, and it's really cool to be able to empower other people to make cool things using your work. And so that's probably the most rewarding part of doing something like this. So that was the Launchpad. And in parallel with that, I was also developing an add-on board. So with the Launchpad, we have these add-on boards called booster packs. And so they're kind of like an Arduino shield. They add extra functionality, and they make it easy to add that extra functionality. So all the hardware design work is already done for you. Just plug it in. Typically, there's some software libraries provided, and you can kind of build off what you're given. So go ahead and pass these around. These are some of the prototypes, both the ones that I kind of built here and assembled here, and then some more Chinese pre-production versions. So that's the white one. And you can kind of pass this around. So this actually has 3 boost converters just like this on this board. So they're kind of slightly different. You know, there's a couple caps paralleled here instead of just one big cap. There's a capacitor here too to act as kind of a decoupling capacitor. But it's the same basic concept here. So we're feeding in 12 volts, and we have let's see, there's 8 LEDs in series. So if you have like a diode, right? An LED is a diode. Okay. The diode has basically a forward voltage drop. So if you apply, you know, like 1 volt here, you've got ground down here, this diode will turn on because the forward voltage of most diodes is 0.7 volts, right? So when you apply a volt here, current starts to flow down through the diode. Well, LEDs, they typically have a slightly higher forward voltage. So their forward voltage is typically anywhere from like 2 to 3.6 volts or somewhere in there, right? And now we actually have 8 of them in series, right? So these forward voltage drops start adding up. So, you know, times 8 or whatever. So if let's round this to about 3 volts, right? 3 times 8, that's 24 volts. If I'm feeding 12 volts into the board, and that's the highest voltage I have on the board, there's no way I can possibly forward bias these LEDs. And for the LED to turn on, it has to be forward biased, and current has to be flowing through it. So what we do is we use a boost converter to boost up. We have 12 volts at the input this time, and we're going to spit out roughly 24 volts. The other thing that's important in this design is that LEDs, they're not current controlled, if you will. If you put, if you forward bias them, as much current as is possible, will try to flow through them. And if too much current flows through them, they blow up, right? So you have to control it. And so that's where the C2000 aspect comes into this, right? What it actually does is it senses the current flowing through the LEDs. So if you look at those boards, actually up here, the top kind of left-hand corner, you'll see these 3 little resistors. And these are called shunt resistors or sense resistors, and all the current flows through them. And when the current flows through a resistor, right, there's a voltage that develops across it. And that voltage is proportional to the current going through the LEDs. So if you sense that voltage, just kind of like we were sensing a voltage here to control the boost converter, this time we're going to sense a voltage, but that voltage is going to be proportional to a current. So what we're actually doing is we're driving a constant current through the LEDs this time, instead of trying to control the voltage with a very fine resolution. We just control the current, and then we can easily control the brightness of the LEDs. So with that, let me demo this real quick. There's some pretty lights. So let's get the power supply. All right, so you plug this bad boy in here. Everything lights up, boots up. And so this actually, the LED booster pack here actually has an Msp430 on it. So an Msp430, that's one of our other processors, and that's what that other launch pad is. One of the things it's really good at is capacitive touch sensing. So you saw there, as I kind of got close to it, the lights kind of flickered around, and that's because it sensed my hand. And I can actually just touch there, and the LEDs will turn on. So there's no physical buttons, it's just like a piece of plastic with some metal behind it. And then as I move my finger around the wheel, I can change the color. So these are RGB LEDs. And you guys can come play with this in a second when I get done talking. Yeah, so fun little project. Not really any real use to it per se, but it demonstrates the technology and what our devices are capable of. And so that's kind of the purpose of this. It's a marketing vehicle to show kind of what we're capable of. And so this was a fun little project that got released alongside the Launchpad last fall. So since then, I've moved on to bigger and better things. So let's see. Let's start with the fun stuff, and I'll go to the work stuff later. So this let's see. This January, TI came up with the idea to do a design challenge for basically anyone on the internet. So the idea was that you would pick a launch pad, and then you would develop a booster pack for that launch pad. And so what also happened is we decided to have an internal design contest. So there was going to be people on the internet designing these, and then we invited TI employees to design these booster packs as well. And so I actually was a little overzealous and entered 2 designs into this contest, and one of them was fortunate enough to win. So I'll start with the one that didn't win. And so that's this board here. And so it's got a launch pad on the bottom, so it's a booster pack. It's one of the larger booster packs that exists today. And what this is a Bluetooth audio amplifier. So you've probably seen, like, maybe a Logitech Bluetooth speaker or some other company's Bluetooth speaker, right? So you connect your phone up to it, and then you can play music to it through Spotify or Google Music or whatever. And so the idea was I wanted to make something like that, but a little bigger and more powerful. So one of the things that I like to do sometimes is go to the river during the summer. So you guys you probably have heard of tubing the river. You probably haven't gone yet since you're not 21. But it's a real fun thing to do. And a lot of people there, they'll have coolers that have speakers on the side of them. So those coolers, they'll have an audio amplifier inside of them, and you can plug your phone into it or MP3 player or what have you, and play music through it while you're floating down the river. That's really cool, that's fun, but no one has one that has Bluetooth. So I was like, oh, why don't I just make a circuit board that does the same thing, but I'll add the Bluetooth functionality in there. So that's exactly what I did. So I actually found 2 reference designs, and reference designs typically, when you find a chip that you want to use, they'll have like a typical design for how you might use that chip to kind of get you started. So originally I had found this audio amplifier chip. So this is a 150 watt Class D amplifier, and this is a switching amplifier. So it works in a similar fashion to kind of what we were showing up here, in that it's very efficient because it switches directly on and off. It doesn't operate in the linear region of a transistor. So I found this. It's 150 watts per channel into 4 ohm speakers, and I wanted to power this thing with just like a normal 12 volt lawnmower battery. But the thing is, this chip, it needs like 24 volts for the amplifier. So I was like, oh crap, I need to find a way to get 24 volts from 12 volts. So I started looking around, and I found another reference design from TI, which was for a 12 to 24 volt 4-phase boost converter. So that's kind of this portion of the board you see here. So I've got an analog control IC, which is what controls each of the phases here. Excuse me. And then out here, it spits out 24 volts. So this is then fed into the amplifier section over here, and powers the amplifier chip. And then I have a Bluetooth module here that I bought. So this is, sadly, it's not a TI solution. But what I did, there's a lot of trade-offs when you're doing a design, right? TI has technology that you can implement this exact same thing here with a Bluetooth. But there's a little more design work that's involved with the TI solution there. So what I did is I decided to go and buy a pre-made module that I could integrate that would be easy to use, right? Because I didn't want to spend a whole lot of time designing that part of it, right? I just wanted it to work. That was what was important in that decision there. So I bought that and put it on there, and actually this isn't the first revision of this design. This is the second revision. You'll see there's actually another spot right here. So originally I had designed this board just to use this other module, which is slightly different size and shape. And after I got the boards and I had ordered the parts, I realized I couldn't get this module. It didn't exist in any of the distributors' inventories. So I was like, darn it, I can't build the board. So I had to respin the board, but I made the design decision here to actually put down both of the modules. So I found another one that would also work, and I put it down, and then I allowed my the ability to actually select which one I wanted to use. So that was another kind of cool thing about this design. So now this one is a lot more expensive, but when this one becomes available, I can easily switch over to using it. So definitely think about later down the road when you're doing more high-level professional designs. Think about availability of the parts and things like that, because it is a very real issue sometimes. So that's the Bluetooth audio amplifier. You can pass that around. And the thing everyone always wants to see is the Quadcopter. So this is the other entry I did in the Employee Design Challenge. And so this is actually the only one that exists today. It's very special, near and dear to my heart. And this looks a lot different than it initially did. So this is the same PCB, but we've changed out the motors, we've changed out the propellers, we've changed out the battery. We're changing out the wireless modules that it uses to communicate. So we've learned a lot from doing this first prototype. And oftentimes that's what you'll find, right? Your first prototype, probably, if you're really, really good and you spend a lot of time and attention to detail, sometimes your first prototypes work. Oftentimes there's problems though, and you learn from those mistakes or the problems with your boards or with your designs, and that's an important lesson to learn. So we originally had different motors and different propellers that were actually a lot shorter than these. So you'll see these actually overlap. The original propellers didn't. I had designed the board for the smaller propellers so they didn't overlap. But once we got all the motors working and everything, we realized we didn't have enough thrust for the thing to fly. So what we did is we looked around at the different motors that were available. We looked at why we didn't have enough thrust. We looked at how fast we were able to spin the motors. And we found that, you know, the speed that the motor spins at, right, it's proportional to the voltage that you apply to it. And different motors have different proportions, right, different coefficients, if you will. So the motors we were using before were, they're called 2000 kV, so basically 2000 RPMs per volt. And we found that we needed more speed. So what we did is we found some motors that had higher ratings. So the ones that are on here are 2900 kV per volt, or kV, so 2900 RPM per volt. And so with that, we also did another thing to allow us to go faster, and that was we upped the voltage of the battery. So originally I had spec'd out like an 8-volt battery, and we actually moved up to an 11-volt battery. So that allowed us to get a little faster. And then the last thing we did, right, is we changed the propellers. So these overlap, but we were able to kind of mitigate that by thinking outside the box, right? So what we did is we added these little spacers here and here that lifted 2 of the propellers to a slightly different elevation than the other 2. So now, when they pass kind of like this, and they don't hit each other. So that's kind of the basics of the story behind the quadcopter. Let's see what else. Communications. So originally, I had intended for this thing to be controlled from your cell phone via Bluetooth. Well, I got, you'll see these headers on here. So there was a Bluetooth module that plugs into this. And I started working on the Bluetooth software, and what I found was the software to make the Bluetooth run was too big to fit into memory. So I was like, oh no, I gotta change this. So I'm working actually with another company that makes a wireless module, and so we're going to change out the wireless that it uses to something that has a smaller software footprint. So that's another thing to consider, right? If you want to integrate some of these advanced communications peripherals or connectivity, oftentimes there's a heavy software requirement, and so you need to, when you're designing something and working something on a larger scale like this, you really need to understand all the different aspects of the project, right? The software aspects of it, the hardware aspects of it. If you're going to go to production, there's a lot of logistical concerns like sourcing the parts, like I showed you on the amplifier board, that really can make or break your design or getting to production. So with that, let's do a little demo of this guy. So it's not remote controlled right now, and this is very much a work in progress. Let me say that. So let's see here. There we go. All right. So now it's just kind of running slow, and I'm going to hold on to it pretty tight because we crashed this thing yesterday. But I've got a guy that's been helping me. He's actually here on rotation from China, and so he's actually done most of the work that you see here. I designed the circuit board, but right now all the software that it's running is work that he's done. So teamwork is another thing that's very important, right? You can't do it all yourself. You may think you can. It's not the case, trust me. A lot of times you need help, and that's okay. That's a good thing. You know, knowing when to ask for help and being humble enough to do that is important. So there you go. It's going. Let's kind of crank it up here. It's pretty light. All right, I'm gonna hold on to it and see if we can go up a little higher. Yeah, it wants to fly now. I need to get a string so I can like walk around like it was some balloons or something, you know? All right, so let's crank this back down here. So that's the quadcopter, and so we're actually working with a company called CircuitCo. And CircuitCo, you've probably never heard of them, but they're actually an important important partner with us. So they manufacture a board called the Beagle board and the Beagle bump. So have you guys ever heard of either of those two boards? No. So it's like a little single board Linux computer, and so this is actually one of them. This is the Beagle bump Black. It actually just came out, and it runs Linux. I mean, you can connect up a monitor and keyboard to this, and this is a computer effectively, and it's it's the size of a credit card. It's got Ethernet. You can plug in Wi-Fi. It's got an SD card here on the bottom. Really cool, fun little board. They're 45 bucks. But they manufacture this, and I'm actually working with them to actually get that manufactured. So I'm really excited to bring that to market and to basically put it out there for other people to play with. So it's completely open source hardware. All the software on it is open source as well. So basically anyone like you guys or engineers or really anyone, right? They can take this and they can hack on it, they can modify it, they can change it to operate how they want. And that's something that a lot of people in the hobbyist community care about a whole lot, because if you can't open up the design and modify it, you don't really own it, right? And so that's kind of another cool, important thing. So yeah, with that, I'm going to go ahead and stop talking. You guys can ask me questions. How about that? Yeah.
So let's say if you turn this on, and I turn my Bluetooth on my phone on, and then play music, it will play?
Yeah. So what you would do, ultimately, right, this is designed to be integrated into a cooler which has some speakers on the side of it, just like normal automotive speakers. And so you connect up 12 volts to these two terminals here. And then you'll see these kind of terminals here with some solder in the holes. This is where you connect your speakers up. And then, yeah, you Bluetooth your phone to it just like any other Bluetooth stereo. And then it's able to play music. Other questions? Yeah?
How long did it take you to make this?
To design this? So, my whole life is what I would say. So, no. What I mean by that is that it takes a lot of learning and effort, kind of before you get to this point, right? So, all that tinkering I did as a kid, taking things apart, reading electronics magazines and stuff like that, going to college, all of that was a very important and crucial piece in being able to do this. Now, to more directly answer your question, this board here, this is the second revision of this board. I would say there's probably a good 20, 30 hours in this board, and probably in the Quadcopter substantially more. The layout tool I use, so the layout is right where you draw all the wires on the circuit board. Let me draw a picture to explain this factor. So if you've got, like, let's say a wire on a circuit board, so this goes off somewhere, this goes off somewhere, and you've got another wire, and you need to basically kind of push this one out of the way. So this is called a shove route. My layout tool doesn't have that ability, so I actually have to manually rip that up, do whatever I want to do with this one, and then I have to reroute this one. And so that makes the process very time-consuming on a board like this, which is very dense. So the density of the components and all the traces on a board like this, if you really look closely at it, is very high. And the more dense and complex your board is, the more time-consuming it is to design.
Who else has a question? You guys could ask him about his college experience,
anything.
How he got his first job, what's the biggest mistake he ever made, what's his biggest success.
Where did you go to college? So I went to a school called Rose-Hulman Institute of Technology, and most people have never heard of it, but that's okay. It's a small engineering school in Indiana, and it's very well ranked, great engineering school. The reason it's not as well known as you would think it would be, though, is because the highest degree that it offers is a master's program. So they exclusively, almost exclusively, focus on undergraduate engineering. So the thing that's really special about that college is the class sizes are pretty small. They're probably what you guys are used to in high school, you know, about 30 students tops. And especially in your higher level classes, you might have, you know, 10, 15 students in a class. And that gives you the ability to talk to the professors a lot more. You know, you can go directly to their office and ask them for help on your homework and things like that. So it's a great little school, very small school, great community feel. I mean, everyone's friends there. When I was going to school there, and this might have changed since, but it was really like a family, right? People like left their dorm room doors unlocked and opened when they'd go, you know, play intramural sports or things like that, because everyone had a mutual respect for each other, and that's I think very important. So, yep, that's where I went to school. Definitely look it up if you're looking at colleges right now. It's a great place. Yep.
So you did 4 years and you got your master's?
I did 4 years. So I was able to get my bachelor's in 4 years, and that's something that's becoming increasingly difficult to do at a lot of schools. But Rose-Hulman, they really try and get you done in 4 years. If I had stayed, they do have a master's program, and I think it's, depending on what you do, it's either a year or 2 years long. And one of the cool things about that school is if you do your undergraduate there and you're in good standing academically, I think you have to maintain a 3.5 through the master's program. But if you maintain a 3.5 GPA, tuition is completely free for the master's. So that's kind of cool. It can save you a lot of money. Mm-hmm. Other questions? Yeah?
How did you start looking for your first job? Like?
For my first job. So at my school they had career fairs, and so I went to the career fairs, and I was not super successful at the career fairs. But basically, how my first job came about. So I was working at a program that my school had called Rose-Hulman Ventures. And what Ventures was, or is a basically kind of consulting engineering department of the school. So industry, they would go out to industry, and companies would basically give them projects for students to do. Excuse me. And then they would hire students to do these projects. And we had, you know, actual engineers that were our project managers that could assist us. And so I worked through this program all through my school, and this was great because I got paid, and I was doing real engineering work, and I could do it during school hours too, so that a really flexible schedule. And so I was working for a guy, J.R. Sima of Sima Software, and I was working for him towards the end of my college career. And you know, I had graduated. I'm looking all through the summer. I'm still working at Ventures. I'm looking, you know, through the internet, any outlet I can find to find a job. And it's 2009. The economy's, you know, in that depression there. I just can't find anything. And it comes to September 1st when school starts, and Ventures said that I could no longer be an employee of the school effectively through Rose-Hulman Ventures. And so JR was happy with the work I was doing. He saw that, you know, I was talented with the software stuff, and he actually decided to hire me to kind of help me out. So I started working for him, and working through him, I got a lot of experience with Texas Instruments parts and Texas Instruments software. And after a while, I had an opportunity to interview with a Texas Instruments FAE. And so I interviewed with him actually there at Rose-Hulman Ventures. And after that, I got a phone interview with a guy out of Dallas. And so that was a technical interview. He asked me a lot of questions about software and hardware and all kinds of stuff. And I did well on that. So then I got another phone call from the guys down here in Houston. And they wanted to fly me down for an interview, an on-site interview. So I flew down here, interviewed with them. They liked me, and I guess the rest is history. So about a month later, I packed up all my stuff and moved down here. And so I think that was around March or April of 2010. and I've been working at TI ever since. Mm-hmm. Other questions?
All right. Oh, no one more.
Oh, don't be shy. Yeah.
Do they like pay you good money?
Yeah. I'm not going to comment on how much I make, but
What would be the average salary of somebody with a 4-year degree out of Rose?
4-year degree out of Rose, the average starting salary when I graduated, and this is across all majors, was I think it was like 58 or 60, somewhere in there. With full benefits, right?